Hello class. In this video, we're going to take a look at some of the basics of an inference procedure called a one-sample t-test. And this is a test that we'll use in scenarios when we want to find a significant difference from a hypothetical sample mean. So we're going to be using this type of a test in a situation where we have quantitative data and want to make a comparison against a hypothetical population value. So like the one sample z-test or one proportion z-test, we have some conditions that need to be met in order to run this type of a test. So if you have quantitative data from a sample and you want to compare that against a hypothetical mean for the population, these conditions need to be met first. And they're really similar to the one prop z-test conditions, just a little bit different in the normal check. So the first condition needs to be met is that our sample is randomly selected or came from an experiment where subjects were randomly assigned to their treatment groups. And that ensures that our sample is unbiased, it's a good representation of the population, and so we can extend our findings to the whole population. The second check is that we need the sampling distribution of X bar to be approximately normal. And there's three different ways that that condition could be met. So I would kind of just start at the top here and just work through and just need one of these to be met. The simplest one is that the population overall already has a normal distribution. So if the population is normal and it's stated, then your sample distribution will be normal as well. If it's not stated anywhere in the problem that your sample is normally distributed, or your population is normally distributed, I should say, then if your sample is at least 30, then your large counts condition is met. The central limit theorem applies. And from that, it tells us that our sampling distribution is roughly normal. And if neither of these two first ones are met and our sample is less than 30, then we need to take a look at a graph of the data and see that it's roughly symmetric and has no outliers. So if we have a sample that's small, less than 30, and we have a really skewed distribution or we have outliers, then our condition checks aren't passed and we are not, it's not reasonable to go through with the test. But as long as one of these are met, then your normal shape condition or your large counts condition is met. And then finally, if you're sampling without replacement from the population, you need the population to be at least 10 times your sample size. You don't have to check that in an experiment if you're randomly assigning to treatment groups, but you do have to check that if you're taking an SRS from a population without replacing those individuals back in. So as long as those three conditions are met, your random sample, your approximately normal condition, and your population size check, if all three are passed, then you're good to go on your test. So next we'll talk about how to calculate the test statistic that we'll use in our one sample t test. So in a previous video, when we learned about the one prop z test, we had learned that the test statistic is always going to fall into the form of your statistic minus your parameter over the standard deviation of the statistic. So in our case, our test statistic will be a t-score. I'll talk about why we use a t-score there instead of a z-score in a minute. Our statistic is what came from the sample. And when we're dealing with means, our sample mean is X bar. Minus the parameter, that's the value that comes from the null hypothesis, which is describing our hypothetical population mean. So that'll be mu. And in the standard deviation, we would use sigma over square root n, but we're probably not going to know sigma for the population. So we would use S, the sample standard deviation, over the square root of n. The reason that we are using a t-score here is because we only ever use a z-score if we're able to know or calculate the population standard deviation. And with a test for proportions, we were able to calculate that directly. P0 times 1 minus P0 over n all in the square root. But here we don't know what sigma is, and there's no way to really calculate what sigma is. our best guess for it is the sample standard deviation. So anytime you're using S and not sigma, you're using a t-score for your test statistic. From this test statistic, you're going to get a t-score, and then there are two ways to calculate your p-value. If you have an inspire, then the simplest way to do this is going to be to use a function called tcdf, which you're going to find in menu 655 in a calculator page. And I'll show you an example of how to use that in just a little bit. If you don't have an Inspire or graphing calculator, then you need to look it up on a table. And the one that you're going to get on the AP exam is called Table B. I know the one I shared with you on Classroom is called Table C, but look for the one that's got the T critical values on it. So let's take a look at an example of where a t-test might be used and take a look at checking the conditions to see that they're met, calculating the t-score test statistic, and then calculating the p-value, either from the Inspire or on the table. So here's the example that we'll take a look at. Let's say we've got a pizza place that normally makes deliveries at an average time of 45 minutes. And let's say that they hire an all new staff and they want to know, is our new staff faster at making these deliveries than what we had in the past? Well, in the past, hypothetically, their true mean delivery time was 45 minutes. And since that's really the hypothetical value that we have, that is our value for mu, which we're going to use in the null hypothesis. So we have this new staff, they've made over 500 deliveries, and so they take a simple random sample of 40 of those deliveries to look up their data on how fast those deliveries were. And in that sample, they had a sample mean of 40 minutes with a standard deviation of 11.8 minutes. So out of those 40 deliveries, their average time was 40 minutes, but it varied from that average by almost 12 minutes. Now, is that enough evidence to suggest that the true mean is now less than it was before? So the first thing we'll do is check the conditions. Since we have quantitative data and we are looking for a significant difference from a hypothetical mean, we would want to use a one sample t-test here to do that, but can only do that type of test if those conditions are met to do that type of test. So first condition to check is that we have a random sample, and the problem says right here it was an SRS of 40, so a random sample condition is met. Next thing that we would need is an approximately normal distribution for our delivery times. And it doesn't say anywhere in the problem that the delivery times in the population were normal. So we don't have any indication about the population shape of that distribution. So instead, we'll have to take a look at our sample size. And in this case, our sample is 40. So our sample is large enough to use the central limit theorem. which means that our distribution, our sampling distribution, should be roughly normal. And then the third check, since we're taking a sample without replacement, is we need the population to be at least 10 times the sample size. Well, the population was 500 deliveries overall, and that is greater than 400, which is 10 times our sample size of 40. So all the conditions are met. Next thing that we'll do is we'll calculate the test statistic and the p-value. So our test statistic, remember the formula for that is that t equals x bar minus mu over s over square root n. Well, the sample mean that we got was 40 minutes, and the population mean, hypothetically, was 45 minutes. And that's over s, which is 11.8, over the square root of n, which is 40. So let's see what we get there with our test statistic. So we have 40 minus 45 over the or 11.8 over the square root of 40. And that's going to give us a test statistic of negative 2.680. So that's how you calculate the test statistic for a one sample t-test. And now let's talk about how to find the p-value. Before we do, we should really think about, is this going to be a one-sided test or a two-sided test? So we're going to get to the full process in the next video and setting up the null hypothesis, alternate hypothesis. What we would do here is our null would be that the mean is 45 minutes. And we'd be looking for evidence to support an alternate. And the question in the beginning was, did their mean time decrease? So under this new step, are they faster? So our null was equal to 45. Our alternate would be, is the mean less than 45? So we're looking at a one-sided test. That's going to be a left-tailed test. Well, here's how you can find the p-value. On the Inspire. So let me pull up the Inspire. All right, so if we go to a calculator page, so we'll open up a new document, we'll go to Add Calculator, where you can find the p-value of using the test statistic that's a t-score. You go into menu 6 for statistics, 5 for distributions, and then 5 for t-CDF. Because remember, our p-value is the area under that t-curve. Well, we're looking at a left-sided test. We're looking for the area to the left side of our t-score. So our lower bound is negative infinity. Our upper bound is going to be negative 2.680. Our degrees of freedom, that's taking your sample size minus 1. So we had 40 in the sample. Degrees of freedom is 39. And then we'll hit OK. And our p-value is 0.005. 0.0536. We'll just go out all the way out there, 536. Now, if you don't have an Inspire and need to use the table that you're provided, let me show you how to look that up. So on the AP exam, you're going to need to download this formula sheet, which has all your formulas and some different tables that you'll need. So if you scroll down to, let's see, table B, and it says right here, table B is the T distribution critical values. So you're looking for this table, T distribution critical values. So what you're going to do is on the left side, you're going to find your degrees of freedom, which would, in this case, be 39. Now, I got a little problem because 39 is not on this table. So remember that even though 40 is closer, you're always going to round down because degrees of freedom is kind of a measure of how much information you have, and you would never round up and act like you have more information than you do. So to err on the side of caution, we're going to look at the degrees of freedom are 30. So you're going to follow this table over to the right until you find kind of a window that your t-score fits into. So we're following this to the right and looking for negative 2.68. So we haven't got there yet. We're at negative 1.31, 1.697, 2.042. As you move to the right, you're getting closer to that value. And over here is where we finally get that window. So negative 2.680. Oh, I should mention that this gives you positive values. So you'd have to take the absolute value, and that's what you're looking up here. So the absolute value would fall between 2.457 and 2.750. If you follow that up to the top of the table, it'll show you the values where your p-value falls between. So on the table, the most accurate we could be is to say that it falls between 0.01 and 0.005. So on the table, is between, well, we'll go lower first, 0.005 and 0.01. And the p-value we calculated more exactly was fit right in between those two values. So even though you don't get the exact p-value here, it does give you enough information to either reject or fail to reject the null hypothesis at whatever your confidence level, or I'm sorry, your significance level is. So because this p-value is very low, it's lower than most of the common significance levels, like 0.05, that's definitely lower than 0.05. And no matter what it is, if it's in this window, it's lower than 0.05 as well. So this would give us significant evidence to suggest that the true mean delivery time has decreased from 45 minutes. So from this video, I'll bring it back to there we go. So from this video, what I want you to be able to do is these two things: check your conditions for running a one sample t-test and calculate your test statistic. And then take that test statistic to either calculate the p-value exactly or at least find a window where that would fit into.